Hello, welcome back to your physics teacher. Today we're looking at section 1.3 from the Nelson textbook, and it is all about displacement. So first we're going to be looking at a single displacement vector, getting the components, then from the components how we can get back the total displacement vector. Then we're going to be looking at how to add individual displacement vectors to get the total displacement vector. And we're going to do another type question where we have one displacement and the total displacement, and we want to find the second displacement. So there's going to be 4 types of questions in total, so feel free to choose which one you want to select from the scroll bar below. So let's get started with question number 4. We have a student who walks 25 meters at an angle of east 30 degrees north, and they want us to determine the components of the student's displacement. So first thing that we want to do is we want to get a quick visual picture of what's going on. And to do this, it's a good idea to consider the bird's eye view. What that means is that we're going to consider a student, and this student walks 25 meters in the direction of east 30 degrees north. But in order to determine east, north, and so on, you need to consider the golden rose compass. Now we can determine the directions. So our displacement vector is 25 meters, and the angle is, if you first start at east, you rotate 30 degrees towards north, and again this was 30 degrees, and we have our displacement vector now. Now that we can visualize this, a good idea is to try to set it up in the coordinate system. In this coordinate system, we're going to use the convention that the y-axis, measured in meters, is actually representing the motion along the north dimension, and the x-axis, measured in meters, is representing the east motion. So that means that the negative axis will be west and south respectively. We're going to redraw our displacement vector with the tail right at the origin of this coordinate system. This makes it much easier to recognize that if you start from the east direction, you rotate 30 degrees towards north in order to get the angle theta of our displacement vector. And this question was asking us to find the components of this displacement vector. So by components, they mean the horizontal and the vertical. The horizontal is going to be along the x-axis, in this case towards the right. So we call this delta dx. And the vertical is along the y, delta dy. And notice that these two are connected head to tail, which suggests that when you add them together, they give you back the displacement vector. And that's the whole reason why we use components. So we have the displacement vector, but we can think of it as the sum of its 2 component vectors, because the component vectors are going to be easier to deal with in other word problems, which we're going to see in this video as well. Now, in order to get those component vectors, we're going to have to look at this diagram again. And notice that by using the convention of the coordinate system, we have just drawn a right angle triangle. So what we're going to do, we're going to redraw this triangle, given that it's right angle, and we're going to take advantage of that to find the components. So now we have a right angle triangle. And if we're going to consider the angle theta, from that angle, this will be the opposite side of the triangle, this will be the adjacent, and this will be the hypotenuse. This means that we're going to be using SOHCAHTOA. Now recall that the length that they gave us was 25. So this means that we need to find the opposite side and the adjacent side, which we're going to take advantage of the sine ratio and the cosine ratio. So let's start off with the cosine ratio. So cosine of 30 is going to be adjacent over hypotenuse. If we were to isolate for the component, delta dx, this would be delta d cosine 30, which we can simplify to be 25 cosine 30 degrees. Plugging this into our calculator, we get approximately 21.6 meters. So that's going to be our x component, or another way we called it the horizontal component. Now for the vertical component, we're going to be using the sine ratio. Sine of 30 degrees, which will be delta dy over delta d. Isolating for delta dy, we multiply both sides by delta d. which gives us 25 times sine of 30 degrees, approximately equal to 12.5 meters. So once you're trying to find the components, you should draw it onto the coordinate system and then take advantage there's a right angle triangle and use SOHCAHTOA. Just make sure you label your triangle with the angle that you're considering, and that way you can find the two components, the horizontal and the vertical component. For question number 5, we have that a vector has the following components: a horizontal component delta dx of 54 meters east and a vertical component of delta dy 24 meters north. Part A wants us to calculate the length of the total displacement vector, and part B wants us to determine the vector's direction. So let's start by drawing the two components that were given. And like before, we should determine the directions based on the golden rose compass. And we want to draw the coordinate system with the same convention as before. The y-axis in this case is in meters, representing north up. The x-axis in meters, and east to the right. So that determines that to the right is positive and up is positive and left is negative and down is negative. Drawing the two component vectors that they gave us, the horizontal component is 54 meters east, delta dx, and delta dy is 24 meters north. Notice that I attached them head to tail, because delta dx plus delta dy gives you back the total displacement. As we saw before, right? Delta d is the sum of its two components, delta dx plus delta dy. And because we are using the rectangular coordinate system, they're going to form a right angle triangle. And in order to get the length of this total displacement, delta d, we could take advantage of the right angle. And because it is a vector quantity, we're also going to have to find the angle theta. So there are two pieces of information we need to find: the length and the direction, because we're dealing with vector quantities. Is the horizontal is 54 meters east, and the vertical was 24 meters north. Once we are able to visualize it, what we're going to do, we're going to redraw the triangle so we can work with the trigonometry and get the unknown side and the unknown angle. To use our trigonometry, we need to first consider the angle theta, the one that we've drawn. And from this angle theta, we can label the opposite side, the adjacent side, and the hypotenuse. This is useful because when we're applying SOHCAHTOA, we can figure out which ratio to use. And because in this case, we have the adjacent length and we have the opposite side, we can find the angle theta using the tan ratio. Tan theta would be delta dy over delta dx. Which we get approximately 24 degrees after we put in the values and take the tan inverse on both sides. We approximate it to be 24 degrees. But because we were dealing with vector quantities, we also need to find the length of the displacement. And once again, recall that we're dealing with right angle triangles, so we can apply Pythagoras, where C is the hypotenuse and we have A and B for the other two sides of the right angle triangle. So C squared equals to A squared plus B squared. C squared is going to be delta D, and the other two are the component vectors. Taking the square root on both sides. And at this point, all we have to do is just put in the values. which we get approximately that it's equal to 59 meters. To find the displacement vector, we needed to find both the length and the direction. So we can state our final answer that the displacement vector is going to be 59 meters, and the direction, since it's going to the right at the beginning, is east, and it rotates 24 degrees towards north. For question number 6, we have a driver travels 15 kilometers to the west and then turns and drives 45 kilometers to the south. Finally, she travels 32 kilometers at the direction north, 25 degrees west. Determine the driver's total displacement. So in this case, we are going to be looking at the bird's eye view again. So we're looking at it from above, and this helps us to visualize the problem. And keep in mind that we're still using the convention that we're going to assume upwards will be north and to the right is east, and both of these are going to be the positive directions. Once we establish this, then we can get a visual of the actual question at hand. So we have a car, and the first displacement that this car undergoes is 15 kilometers west, delta D1. And the second displacement, the driver turns and drives 45 kilometers to the south, delta D2. And finally, she travels 32 kilometers, and the direction is going to be starting from north, 25 degrees to the west. So let's get the angle first. This is 25 degrees north, 25 degrees west, and that's going to be a displacement of 32 kilometers. We can call this delta D3. And to determine the total displacement, all we need to do is connect the initial position to the final position. So the initial one is where the car started and where the car finished. Right, because the displacement measures the change in position. So if we want the total displacement, we want the total change in position. So from the very final position to the very first initial position. And the direction is towards the final position. So we have to put the arrowhead there. So in order to determine this total displacement, we can call it delta dt, and that's our unknown. But because it is a vector quantity, we also need to find the angle. In this case, we could start from the horizontal, and we're going to call this theta. So we don't know that angle. So we can redraw this total displacement vector. And notice that here, the x component is towards the left, and the y component is towards downwards. We can call it delta dtx. And delta dty. And again, we're going to use the angle theta to be from west towards south. But because now we're dealing with displacement in 2 dimensions, one way we can find the total displacement, we're going to just add all the displacements that this car underwent. So in other words, the total displacement is the sum of the first plus the second plus the third. And because we're dealing with vectors, and vectors have 2 dimensions, we can break this down into its components. So in order to find the sum, we can find the sum along the x, and we can find the sum along the y. So we can rewrite this along the components. Now it does look very complicated at this point, but recall that to get the individual components of the total displacement is by adding the individual components of the other displacements. So what do I mean by that? Notice that if we go back to our diagram, along the x, we have delta d1, and we add to this delta d3x, the component of it, because delta d2 was only pointing downwards, so that's why we didn't include it here. Because delta d3 is along the y component, but notice that it was going all the way downwards. But the component of delta d3 was a bit upwards, which is why you end back to the delta dty where it was. So this is just a way to verify that we can just, to find the total displacement, we can add the components separately, then we build back the total displacement vector. Okay, so we can simplify our x components. Delta d1x is just delta d1 itself, and because it's pointing to the left, we have to put a negative. Delta d2x only had a y component, so along the x, it will be 0. And delta d3x, it was pointing to the left, so we have to put negative delta d3x. And our total displacement along the x was pointing to the left, so we put it as negative. We can simplify this by dividing both sides by the negative to give us this expression. Now let's simplify the y components. The total displacement along the y was pointing downwards, so we put a negative. The delta d1 had no y component, so that would be 0. Delta d2y was only pointing downwards, so it's going to be negative 45. And delta d3y was pointing upwards, so we're going to put a positive. So delta dty equals to 45 minus delta d3y. Good. So now at this point, notice that we're going to have to find the components of the third displacement, delta d3x and delta d3y. So in order to do that, we're going to have to redraw the triangle for the third displacement and find the x and y components. In order to do this, we have drawn a right angle triangle, and we're going to take advantage of SOHCAHTOA. So here we're going to use the sine ratio and the cosine ratio. Sine of 25 is going to be opposite over hypotenuse, and cosine of 25. Cosine of 25 is going to be adjacent over hypotenuse. So relative to the angle 25 degrees, the opposite side, the adjacent side, and hypotenuse. So we should label it to help us out. And at this point, we just put in the values to isolate for it. And those are the horizontal and vertical components. So we found an expression where if we were to put it into the calculator, we could find the value for it. But instead, let's go put it back into the expression we had above. So our total displacement along the x is going to be 15 plus 32 sine 25. And our total displacement along the y is going to be 45 minus 32 cosine 25. So this we get approximately 15 plus 13.52, which is approximately 28.52. for the total displacement along the x, and along the y, 45 minus 29, which is 16 for the total displacement along the y. So now that we have the components, we have to build back the total displacement vector. So recall that the x was negative, so delta dtx, and the y was negative, delta dty. So our total displacement vector, delta dt, will be the hypotenuse. And the angle we're looking for is from west rotated towards south. So we're going to call this angle theta. Again, we're going to end up using trigonometry for right angle triangles in order to solve for the hypotenuse and the unknown angle. So we're going to take advantage of the Pythagoras theorem and the tan ratio in this case. So if we're going to use Pythagoras, recall that it's c squared equals to a squared plus b squared, because we're dealing with right angle triangles, where c is the hypotenuse and we have a and b as the other two sides. So delta dt squared, we get approximately 33 kilometers. You could verify that for yourself. And using this angle theta, this would be the opposite side and this would be the adjacent side. So we have tan theta equals to 16 over 28.52. Taking the tan inverse on both sides, we get approximately 29 degrees. So now we can just finally write our concluding statement. So the total displacement vector has a magnitude of 33 kilometers and the direction is going to be west 29 degrees to the south. Now for question 10, we have that a car takes a trip consisting of two displacements. The first displacement is 25 kilometers north and the total displacement is 62 kilometers at an angle of north 38 degrees west. They want us to determine the second displacement. So like we've done before now, you should try to visualize this from the bird's eye point of view, so just from above. And keep in mind that we're going to set the convention that upwards is north, to the east is to the right, and both of these are going to be positive. So any vector that points to the left or downwards will be negative. So let's try to see if we can visualize this. The first displacement from where this random car started, so first let's draw a car. The first displacement is 25 kilometers north. And they don't tell us the second displacement, that's what we're trying to find, but we know that the total displacement is at an angle of north 38 degrees west. So if we recall, the definition of total displacement is from your starting position to your final position. So that's what the total displacement vector measures. Delta dt, this is our unknown. No. We know the total displacement. North 38 degrees west. What we don't know is the second displacement. But we know that the second displacement is from the ending of the first towards the final total displacement. So delta d2 is our unknown. That's what we're going to try to find. And if you recall, we have a formula. The total displacement is equal to the sum of the individual displacements. But because these are vector quantities, we can break this calculation down into two components, along the x and along the y. Now, because we are working with components, this means that our vectors that we were given, it is a good idea to break them down into the x and along the y components. So you need to draw a triangle for each of the ones that we were given. So we're going to draw the triangle for the total displacement. And notice that for delta d1 is just pointing up, so that one we don't have to worry about the x component. So let's simplify that first. Delta d1x is going to be 0. Delta d1y is going to be positive because it points up, so we could take it as positive 25. So let's rewrite these equations. So notice that the total displacement along the x equals to the second displacement along the x. And for the y component, the total displacement along the y is 25 plus the second displacement along the y. So here we have two equations so far. So as I was mentioning before, a good idea now is going to be to break down the total displacement vector, and then we're going to substitute into these equations in order to get our next quantity. Notice that we have a right angle triangle because whenever we're dealing with components, they're on the rectangular coordinate system, which is always going to form right angle triangles for the components. This means that we can take advantage of SOHCAHTOA. And from the angle 38 degrees, we're going to label the opposite side, the adjacent side, and the hypotenuse. And this is going to be useful in order to find the sine ratio and the cosine ratio of 38 degrees. So here we have found the two components, which means we can plug it back into the equation that we were using before for delta dtx and for delta dty. But we are dealing with vector quantities, so we still have to consider the directions. Delta dtx is pointing to the left, so we're going to have to take it as negative, and delta dty is pointing upwards, so we're going to have to take that as positive when we're putting it back into the formula. Delta dtx was to the left, so we have to put negative 62 sine of 38 equals to delta d2x. Delta dty was pointing up, so we take it as positive, so 62 cosine 38 equals to 25 plus delta d2y. So now we have our second displacement along the x component. It's just going to be negative 62 sine of 38. And we can isolate for the second displacement along the y as 62 cosine 38 minus 25. And now let's just substitute this into a calculator and see what we get. Negative 38 along the x, and along the y we get positive 24. This is going to be useful because the question was asking us to find the second displacement, but now the only thing that we have are the components. This means that we need to reconstruct our total this means that we need to reconstruct our second displacement vector. Our second displacement vector, the x component points to the left, and the y component was pointing up. So we can reconstruct the second displacement. Delta d2. And the angle, we can give it from the west, rotated towards the north. So we can call this angle theta because we don't know what the angle is yet. So it's our unknown. But once again, because whenever you deal with components, you are dealing with right angle triangles, so we can take advantage of the Pythagoras theorem and SOHCAHTOA. So SOHCAHTOA is going to be useful to find the angle, and the Pythagoras to find the magnitude of the displacement itself. Using Pythagoras, we're going to take C to be the hypotenuse and the other two sides A and B. Recall it's going to be C squared equals to A squared plus B squared. This means delta D2 equals we get approximately the hypotenuse is 45 kilometers. And for SOHCAHTOA, considering this angle theta, the opposite side and the adjacent side, normally you should be using tan ratio. So we have tan theta equals to theta is approximately 32 degrees. So now in order to write our second displacement, it is a vector quantity, which the magnitude is 45 kilometers. And the direction, we started from west and we rotated 32 degrees towards the north.